Hey guys, so welcome to the second video in our chemistry series. So in this video, we're going to focus on introducing the periodic table, and we're going to take a look at trends in the periodic table. So let's jump into it. Okay, the periodic table. This is an example of a periodic table. There's heaps out there, but I like to use this one in particular because it gives us a very clear reference of the different types of elements. There are the standard things like the atomic number, the symbol, the name, and so forth, but then it also color codes them according to different groups. And so you can sort of see here, each one of these elements, depending on what color they are, correlate to a type of group down the bottom that you can sort of see there. Now, one of the easy things to sort of do and mark your periodic table to sort of help you understand the trends is actually to mark them across the way that I have here in red. So what I've actually done is I've actually numbered the groups down 1, 2, 3, 4, 5, 6, 7, and 8 up the top there, ignoring the bracket of the yellow group in the middle, which are your transition metals here. And then what I've also done is running down each row, I've labeled them 1 to 7, 1, 2, 3, 4, 5, 6, 7 as well, identifying all the different rows. Now, one of the key things to understand about the periodic table is what we call the lanthanides and the actinides. Yep, everything on the periodic table here is displayed as it is for a particular reason, and so part of that reason is also to make sure that you guys are well aware that numbers 57. Atomic numbers 57 to 71 are your lanthanide series elements, which are all this entire row squeezed together inside this little bracket because they all exhibit a very similar property in terms of the element and the way the element interacts. And then what you've also got are the actinide series, which is numbers 89 to 103, all squeezed inside this little bracket here. So you can think of it as lanthanides beginning with lanthanum all inside here, and actinides beginning with actinum all inside this little group here, and then the pattern continues as per normal. Okay, now the periodic table is sort of set in that particular way, and what I've done is I've labeled it in this particular way to follow the old model in which we understand how electron shells work and therefore how they interact with one another. So what I'm doing is I'm intentionally ignoring the transition metals and are not labeling them in the group section at the top, and only with the period section on the side here. Okay, what is the periodic table? The periodic table shows the arrangement of all the known elements in the entire universe. Now, the arrangement it's not random. It doesn't happen the way that it is, but it has a distinct and complex pattern. The reason why, if I was to go back, the reason why the periodic table is arranged like this and not in a 10 by 10 or a 10 by 12 grid is because by understanding it in this particular pattern, you can actually understand some of the properties that the elements actually have. And the reason why it runs across from 1 to 8 and not 1 to 10 is for a particular purpose, which we'll have a look at in the following videos later on as well. Okay. Now, it's called a periodic table of elements and not periodic table of atoms because the element represents the entire species of an atom. Just like how you would expect, for example, when we say the word lion, lion both represents one animal, a lion, a single organism, the lion, and it also represents the species of lions. So if you think about element, the word element is like the word species, but for chemistry, for atoms. Okay, so when we say, for example, hydrogen, we are both referring to a single atom of hydrogen or the element hydrogen represented by all the individuals within that species. Okay, now just to make things a bit makes a bit more sense for you guys, when I say elements of the same group, what I actually mean is the entire column of elements belong to the same group. Okay, and when I'm talking about rows of elements, we're talking about them as periods. Okay, and so by understanding this arrangement of groups and of periods, you can then identify chemical properties of the different elements. Okay, so for example, all the elements here, they're in group 2, and in the way that I've set the periodic table, the 2 at the top here represents that beryllium, magnesium, calcium, strontium, barium, and radium are all in group 2. Okay. That also brings us to this part where the transition metals, which I have intentionally left out, don't belong to any particular group number. In actual fact, with the updated periodic table and the actual element ring represented in clouds, they do belong to a group, but for the purpose of this model, I've ignored those groups, okay? And then all the elements in the same row belong to the same period. So all of these belong to period 4. Hydrogen and helium are the only ones that belong to period 1 because they are the only ones in the top row. And then these ones here belong to period 2, 3, 4, 5, 6, 7. Okay, and you don't have any more in period 7 because there are no elements belonging to an 8th period. Okay. Oh, by the way, since the time that this one was released, which is in 2015, the unknown elements here, and here have all been actually discovered, and so the updated periodic table will have new elements that have already been discovered there. Okay. Now, how do we read a periodic table? Well, the key thing is that in the previous video, I taught you guys how to identify the electron configuration of the atom based on its atomic number. So if you know the atomic number of an element, you can actually figure out how many electrons and how many shells that it actually has. There's actually a quicker way of doing that. Rather than just using the atomic number and then calculating how many electrons and then calculating the electrons fitting into the 2888 octet rule, you can actually use the period and group number to get a really quick reference on the properties. Okay, so this is what they represent. The period number tells us how many shells the atom has. So elements in period 3 will have 3 shells always have 3 shells. Elements in period 7 will have 7 shells. Okay, and so the period number is useful for telling us the number of shells that the atom has. The group number will tell us how many valence electrons are in the outer shell. So valence electrons being the electrons in the outer shell. Okay, now it's worth noting here that we are still ignoring the transition metals. Okay, but elements in group 1 will have 1 valence electron, 1 electron in its outer shell, like hydrogen. Elements in group 8 will have 8 electrons in their outer shell. The only exception to this is helium, which sits in group 8 but has only 2 shell electrons in its outer shell. Okay, all the other ones will have 8 electrons in its outer shell, and then everything in between. Elements in group 4, for example, carbon is in group 4 will have 4 valence electron, and then magnesium will have 2 valence electrons, and so forth. Okay, we ignore the transition metals, but most transition metals will actually have 2 or 3 electrons in the outer shell. Okay, now here's your periodic table of a different kind, and they all occupy certain groups, and they're shaded or color coded according to these groups. This periodic table here has them sitting in this little key here, but they all have a certain set of properties. Okay, so everything in group 1, we actually call those the alkali metals. The only exception being hydrogen, because hydrogen isn't really a metal. Okay, it's a non-metal element. Everything in group 2 are what we call the alkaline earth metals, which are still metals, but they are more abundant in the earth. Everything in this middle bracket here are called the transition metals. Everything here are called the metalloids. Everything here are called the non-metals, and the ones in here in red are actually called semi-metals. And then we've actually got a few more as well. For example, these ones here are called the halogens, and then these ones here are called the noble gases, yeah, being part of the non-metal group. Okay, hydrogen over here is a non-metal, even though it sits in group 1, because hydrogen is a bit of a special element. Because it only has 1 electron, it exhibits a very particular type of property, which we'll go into when you explore chemical bonding. Okay, trends that you will notice in your periodic table. Alkali metals, elements in group 1, are what we call extremely reactive metals. Okay, they will very easily lose electrons to other atoms and will naturally react with things like water to form an alkaline solution. Okay, the key word here is lose. Yeah, keep track of this because I'm going to come back to this in a second. Alkaline earth metals group 2 are very reactive. They're not as reactive as alkali metals, but they are still reactive, and they will also lose electrons, and they're found in the earth in abundant proportions and are also react with water to form alkaline solutions. The transition metals in the majority of known metals are called transition metals, and usually have a range from about 1 to 3 valence electrons, and they will also prefer to lose electrons. Okay, your metalloids, which are your funny looking triangular bracket in the on the right hand side, they have some properties of metals, and they will lose electrons, but as you go further down, the larger they get, the less they tend to do so. Your nonmetals will mostly gain electrons. Your halogens, which are a nonmetal, are extremely reactive nonmetals and really wants to gain electrons. So just like how the group 1 alkali metals really want to lose their electron to giving it away to other atoms, your halogens, your group 7, really want to take those ones and put them together. Okay, you will notice that if you ever listen to the periodic table song by ASAP Science, that one of the lines in the chorus is that alkali and halogens react aggressively. Yeah, in that if you put an alkali metal, a group 1 element, together with a halogen, a group 7, the group 1 really wants to throw away that electron, and the group 7 will really want to take it, and you get these great big chemical reactions that occur. Okay, finally, your last group, your noble gases, group 8, they are what we call inert. Inert means they don't react, and they occur naturally in nature as being extremely stable, and they will sort of just float on their own. For example, helium gas is an extremely stable gas. Helium won't burn. You can't burn helium the way you can burn hydrogen, because helium is already stable and it won't react with anything. Back in the old days, what they used to do before they made helium blimps and helium based I think they're just called blimps. They used to do it out of hydrogen, and then one of the issues, for example, the Hindenburg disaster that happened a while ago now, it happened because their blimps were filled with hydrogen, and hydrogen will react and will burn up, whereas helium doesn't, which is why now it makes sense. Most things, if you want something to be buoyant and lightweight, you fill it with helium and not with hydrogen. Okay. So there you go. There's your groups. Now, you will notice in the trends that your metals, your alkali metals, alkaline earth, your transition metals, and your basic metal and your semi-metals, they're all called metals. And the reason why they're called metals is not because they have the properties that we usually expect metals to have, being shiny, strong, and conduct electricity and all those kind of things. Even though that is part of being a metal, they are called metals because metals are elements that give electrons. Yeah, they give electrons to other elements, and so that's the definition of a metal. Whereas the definition of a non-metal is any element that is willing to take electrons. Okay, it will take electrons from other atoms rather than give. So your metals will give electrons, and your non-metals will take electrons. Now you will notice here that group 8 here do not belong to either give or take, because when you are in group 8, you have a full outer shell. You have either 2 or 8 out in your outer shell, and therefore you are stable energetically, and you don't need to take or give electrons to become stable. Okay, and we'll talk about that a bit more when we go into chemical bonding. Okay, now other trends. One of the other trends that you will notice about periodic tables is that the elements, as you go down the group, you will increase in size, right? And the reason why they increase in size is because they increase in the number of shells they actually have. Elements in the first period, like hydrogen and helium, only have one shell. Elements in the second period, such as let's say sodium, for example, or magnesium, will have. Oh no, hold on. Sodium will have 3 shells. Lithium or carbon, they all have 2 shells, and so having 2 shells makes the atom larger in size than those with only 1 shell. Okay, period trends. When you go from the left to the right, you might expect that because you're increasing the number of protons, electrons, that it gets bigger, but it actually doesn't. It actually gets smaller. So elements actually decrease in size from the left of the periodic table to the right. Yeah. So for example, sodium with an atomic number of 11 will actually be bigger than magnesium, which has an atomic number of 12. And the reason is because the increase both in the number of protons and the number of electrons will attract each other even more and makes the atom much more compact. If you have 11 protons and 11 electrons in sodium, those 11s will be attracted to one another. But if you have 12, you have 1 extra proton and 1 extra electron. That's 1 extra plus and 1 extra minus, making it much more attracted to one another and more compact. And that's what you actually look like. The periodic table looks like if you were to look at the size of the atom. Yeah, you can sort of notice there that as you go down, you increase your outer whole shell, but then as you move from left to right, you get smaller. So for example, there, potassium is much, much larger than calcium, which is larger than scandium and titanium and vanadium and all those kind of things. And then when it gets to the end, it gets really, really small because you've got so much attraction forces between the protons and electrons that when you pop onto the next period, you gain a new shell, and therefore the size increases once again. Okay, and so that's the general trend of there. Now this photo is missing group, period 7 atoms. So just be aware of that. You're missing the last one. So the smallest atom or the smallest element in the periodic table is actually helium, not hydrogen. And the largest is actually francium, which is down here. You can't really see it because it's not there. But francium will be down here, and that's the largest element in terms of size, not in terms of atomic mass. Okay. So that's it for the periodic trend. Next video, we're going to look at chemical bonding, and then we'll look at how these, all the stuff we've been setting up for you guys up until now, come together in the way that atoms will interact with one another. Okay, I'll see you guys then.